All right, welcome. We're going to start talking about Riemann sums today. All right, Riemann sums are just a generalization of this approximating area under curves that we already had. So the old picture was this. You had a function f over some interval a to b. You wanted to approximate the area. So you divided it up into a bunch of intervals of width delta x. We grabbed the right-hand side here, for instance, to make rectangles. And then we added up the area of the rectangles, and it approximated the area under the curve. So the area under f was approximately given by this thing we called r sub n, which was defined to be the sum from j equals 1 to capital N, f of xj delta x, where your thickness, your delta x, was b minus a over n, and your xj's were just a plus j delta x. All right, that's all fine and dandy, but Riemann sums are very much like this. The only difference is they allow you to have variable thicknesses, delta x, and they allow you to pick any point in this interval and use that to go ahead and make the height of the rectangle. And really, that's the only difference. All right, it involves some notation. First of all, we need to pick those divisions of a to b into the x sub j's. That's called a partition. So a partition of size n of ab is just a selection of points where x naught is a, and then the next point is x1. You pick something bigger, x2, and so forth, until you get to x sub capital N, the last one, which has to be b. So you should think of it as this, a to b. You've got some, this is x naught, this will be x1, this will be x2, x3, and so forth. We define the delta x's just as the width here. This will be delta x1, this will be delta x2, and so forth. So the general formula is that the delta x sub j will be, let's see here, x sub j minus x sub j minus 1. And then you're allowed to pick a sample for this. And that just means you pick any point in the first interval, C1, any point in the second interval, C2, any point in the third interval, and they can be the endpoints as well if you want. So C sub j just has to be in the interval going from xj minus 1 to xj. All right? And if you have all that, then you can approximate the area under a curve. So let me draw it again over here. So suppose now we have our function f here. And we've got a to b. And we have a partition. So this is x0. This will be x1, x2, x3, and so forth. And then you have to have a sample. So you have a C1, C2, C3, and so forth. And you use these sample points to get the height of a rectangle over each of these guys. Use that to make the rectangle height. And so forth, all the way on. And so the Riemann sum will just be the sum of the areas of these rectangles. Okay? So that first rectangle, I'm going to call it just R now for Riemann sum. Well, the height of the rectangle is just, how high is that point? It's f of C1. How high is this one? F of C2. How high is that one? F of C3. So the area is the height, f of C1, times the thickness. So the width here was delta x1 The width here was delta x2. So it would be delta x1 plus f of c2, which is delta x2, plus you keep doing this until the very last one, f of cn, delta xn. So that's the long form. The short form is just this. The Riemann sum is the sum from j equals 1 to capital N, f of c sub j, delta xj. All right? Where the delta x's come from the partition and the cj's come from the sample. All right. We'll talk about some properties of this and some concrete examples in a bit. See ya.